Then we said when we have less amount of air, that means that we have less amount of oxygen. We got carbon. We got carbon, then plus oxygen. This time it is less. And instead of getting carbon dioxide, this time we got carbon monoxide, which is also a gas. So here we put a 2, here we also put a 2. So basically that is what we looked at in the last lesson. And again, we need to know that carbon dioxide is the same as carbon 4 oxide. Carbon dioxide is the same as carbon 4 oxide. Why do we call it carbon 4 oxide? Is because carbon has a valency. Carbon has a valency of 4, and also oxygen has a valency of 2. So when we switch the valencies, given that carbon has a valence of 4, then it means that this one goes in 4 by 2. Then we come up with carbon dioxide. But again, we can call carbon dioxide carbon 4 oxide. So in case you hear me talking about carbon 4 oxide, it is the same as carbon dioxide. Then we can call carbon monoxide, we can call it carbon 2 oxide, whereby carbon this time round is using a valency of 2, and also the oxygen is using a valency of 2. And remember, when the valencies are the same, we just ignore, or even though we cancel and we get 1, when we are doing these chemical formulas we don't write 1. So we end up with carbon monoxide, or what we call carbon 2 oxide. So those are some words we shall keep on hearing as we move on. I saw some hands. Yes, Agatha or Wasma?
Yeah.
Okay, then Agnes. Agnes, I'm not able to hear you.
Excuse me, Mr.
Yes, please.
On the form saying carbon with the valence of 2, isn't it 4?
No, carbon can have 2 valences. It has 2 and 4, but the valence of 4 is the one which is stable. But it has 2 valences. It can use a valence of 2. That is when it forms carbon monoxide. It means it's using a valency of 2. It can also use a valency of 4. So it has 2 valences, and that's why we are able to have carbon 4 oxide, or to have carbon dioxide.
Okay, Mr.
Vale, you're welcome. Members, it's like how we have, if you are talking of the valence of carbon, it has 2 and 4, but normally it uses 4, because 4 it is the stable one, the one which forms stable compounds. That's why most of us are used to 4, but it has 2 valences. Just like how we have copper. Copper, we say it has variable valences. It has 1 and 2, but it forms stable compounds in valency of 2. That's why the compounds of copper, you find that we have like copper 2. We have like copper 2 oxide, meaning that in copper 2 oxide it is using a valence of 2. It is using a valency of 2. As long as we put something in the bracket, it means that that metal has got a variable valence, so it has more than 1. I didn't want to go deep into that, but what you should know is that copper has 2 valences, but commonly it uses 4, the one we are used to. Someone is saying that my voice is too low. I need to check your network, maybe. Okay. Namatovu, you can raise up your hand and you tell me exactly why you didn't understand. Namatovu Jovia, raise up your hand and you tell me where you actually didn't understand. Okay, so you're late. We are trying to save time. So let's continue. We want to look at the chemical properties again, and this time around we are looking at reaction of metal oxides with the carbon. Reaction of metal oxides with the carbon. So what we shall do, we're going to look at those reactions where copper is reacting with some metal oxides. So we say that carbon readily removes oxygen from oxides of metals lower than it in reactivity series. So we have specific examples or specific oxides which can be reduced by carbon. And in this case, if we say that carbon readily removes, if we say that carbon readily removes oxygen from oxides of metals lower than it in the reactivity series, we can as well say that we can as well use this word here that I've just circled. We can as well say that carbon reduces oxides of metals lower than it in reactivity series. So we can avoid these three words. Instead of using readily removes oxygen, we can say reduces oxides of metals lower than it. The condition is that those metal oxides or the metals must be lower than carbon in reactivity series. They must be below it. In other words, if it is carbon, then the metals must be lower than that carbon. If they are above, then we cannot have the reaction. Yes, Priscilla? In case if you raise up your hand, please make sure that if I say unmute, unmute very fast so that we can move on.
Excuse me, teacher, I can't hear you well.
Maybe it could be a network.
Okay.
Okay. Agnes?
Excuse me, Mr. What is a reducing agent?
Okay. A reducing agent, we can define it as, according to what we have here, we can say a reducing agent is that substance that readily removes oxygen from compounds. So we can even use this statement. A reducing agent is that substance that removes oxygen from other compounds. Let's have Lillian.
Sure.
Yes, please.
Java is too low.
Okay. Let me see what I can do.
Yes.
All right.
Mm.
Jovia.
So what's the meaning of reactivity series?
That is the arrangement of metals or non-metals in the ascending order of their reactivity. Of the descending order, not ascending, of the descending order of the reactivity, how they react in that order, but descending one. In other words, we start with the most reactive, like potassium, then we go down to the least reactive, which is, I think, which is gold. So this is the arrangement of elements in their descending order of their reactivity. Okay.
Yes.
Yes, Mugabe.
Good morning, sir.
Good morning to you.
So I was asking the pattern of the definition of reducing agent and reactivity series.
A reducing agent, we say that is a substance that readily removes oxygen from another compound. Reactivity series, we have said that the arrangement of elements in the descending order of their reactivity. Clear?
Yeah.
Then Deborah.
Excuse me, teacher. In the definition of reducing agents, they say an element that can remove oxygen from a substance or add hydrogen. Does carbon also add hydrogen? Since it's a reducing agent.
We have different reducing agents. We have different reducing agents. There are those ones which can add hydrogen, or there are those ones which can remove oxygen. It depends on what that reducing agent has. If it contains oxygen, then it will if it contains hydrogen, then it can add it to another element. If it doesn't, then meaning it must be removed. It must remove oxygen from the other element. Like how we normally define reduction, we can define reduction in different ways, in 3 different ways. One, it is the removal of oxygen from a substance or a compound, or we can define it as the addition of hydrogen to a compound or a substance, or we can define reduction as the gaining of electrons. So those are the 3 ways that we can define reduction. So once again, it depends on which reducing agent you're using. If it contains hydrogen, then to be able to add it to the compound. I don't know what's wrong with my voice, but let me see what I can do. How many people are not hearing me well? So that we can rule out the option of network. In case you're not hearing me clearly, you can raise up your hand. Let me see how many hands. Okay, let me see what I can do. For me, I thought that I'm even shouting. How about now? Am I now audible? Hello? Someone can say yes or no? I'll try to change my microphone. Okay, so we can go with that. I like that somehow. At times it could be your network. At times it could be your network. If you don't hear me, you just need to change your position if it is network. So that is let's continue and say that thus it acts as a reducing agent. So our carbon acts as a reducing agent, and we have defined this one in different ways. Someone says that is addition of an element or substance that adds hydrogen to another substance. So let's continue. So these are the examples. These are the examples of oxides which are reduced by carbon. These are some of the examples of compounds or oxides in this case, which are reduced by carbon. So we have zinc oxide. This is the formula for zinc oxide. We have lead 2 oxide. Whenever we put the valence in the brackets, like I said, it means that that element or that metal has more than one valence. Take an example of this lead 2 oxide. Lead has 2 valences, just like how we talked about carbon. It has a valency of 4 and also a valency of 2. And for us, we are used to this 2. That is what we do at O level. So we are used to this, to the 2, that valency. So, but it can also use 4, as we shall see in the near future. Then also have copper 2 oxide. Once again, I say that copper also has variable valencies. It has 2 and 1. Then we have also iron 2 and also iron 3. So you can see that here we are using different valencies. So iron can have a valency of 2 and also a valency of 3. So remember, these are some examples of oxides which are reduced by carbon. So that is the reaction equation. We are having zinc oxide reacting with carbon. Then zinc oxide will be reduced. It will be reduced to zinc. This means that carbon took away this oxygen, or we can say it removed the oxygen. So the oxygen was now transferred to let's remove this arrow. The oxygen was transferred to carbon, and that's how we came up with carbon dioxide gas. So the zinc remained as a metal. Then we formed a gaseous compound or a gaseous product of carbon dioxide. That's what we call reduction. So in this case, carbon reduced zinc oxide, and in doing so, for it to get oxidized. Now we are bringing another term of oxidized, and that is where we get oxidation, the addition of oxygen to a compound or an element. So our carbon, which had nothing here, after removing the oxygen from zinc oxide, it was added to itself, meaning that it was oxidized to carbon dioxide. Let's hear from Alicia. Yes, Alicia.
I had forgot to what?
To lower your hand?
Yes.
Okay, sorry about that. Yes, Mugabe.
So I'm requesting to turn back the examples of oxides reduced by carbon.
I think they are there. Don't worry, we shall have this presentation. I will send it to your notes at your classroom. So don't worry, you'll find it there. Otherwise, if we keep on going back, going forth, then we shall waste a lot of time. But maybe for the last time. But whatever we have on screen, we shall share it. We shall have our own copies. So these are examples of oxides reduced by carbon. So these are the ones. Good morning, Chrissy. I saw some hands. Okay, we can continue now. So that is our first equation. We are using zinc. Then the second one, we are using copper. The same thing is happening. Maybe what we should add on is that the color of zinc. The color of zinc here, we are using heat, so we need to heat zinc oxide in carbon. So the color of zinc, when it is cold, it is a white solid. When it is hot, it is a white solid. Then when it is hot, it turns yellow. When zinc oxide is hot, it is yellow. Then zinc here is a gray solid. Zinc metal is gray in color. Then this one is a colorless gas. Normally ask us these questions to write the observations. Observations, that is what you write, what you see when a reaction is taking place. So given that we involve heating, once heating is involved, then the white solid will turn to yellow when it gets hot, and we shall form a gray metal and also a colorless gas, which is carbon dioxide. You can go on and test for carbon dioxide. First of all, carbon dioxide does not support burning. So if you put a burning splint or anything burning, the fire will be put out. Or we can use calcium hydroxide, which turns milky. Vivian, you're saying that sometimes you receive a Form 1 work. I'm not sure about that. Maybe you need to check when. You might find that you got senior 1 classroom. Let's hear from, there is someone who raises up her hand and then she goes down. Cravens, something like Cravens. I don't know whether you are testing your hand. Yes, please.
Excuse me, sir.
Yes, please.
The carbon on the left side, is that equation balanced? I thought you're supposed to add there too.
Let me check. This one, Cravens, you can unmute
Yes,
yourself. Let's check it out and see.
Yes.
You are talking about this second equation,
Yes, the carbon.
This carbon here. Oh, you are this carbon.
Here there is a 2, but then when you go on this side, it's only 1.
Okay, maybe. Let me see. You can show me. I've given you the rights to annotate on the screen.
Here, sir. This carbon, and then there is also this one.
Right there. You have that chance. I've given you that permission. I don't know whether you know how to do that. Okay, it seems you failed to do it, but so if I'm to check, let me check the whole equation. If I put a 2 here, it means that we shall have 2 copper atoms and also 2 copper atoms this side. Then for oxygen to be 2 times this 1, so it will be 2, which is here, then times the 1 oxygen atom, which gives us 2 atoms of oxygen. And also here we have 2. We already have 2 this side, copper 2, rather oxygen atoms. So according to me, I think the equation is balanced, because here carbon we have 1, and also here we have 1. Maybe if you are confusing the C of carbon symbol with the C of carbon, The symbol for copper it is Cu. Then the symbol for carbon it is just C. So these two are different.
Okay, sir.
Okay, you can mute yourself. So we can have another equation. Also for copper, for lead 2 oxide. So this is lead 2 oxide with copper. Then we form lead, metal, and carbon dioxide. Once again, the color for copper 2 oxide this is a black solid. This is a black solid. This is a black solid, and by the way, carbon is also black. Carbon is also black. Then we are forming a brown solid. So copper as an element or as a metal, it is brown. Just like how you look at copper wires, they are brown. And again, carbon dioxide is a colorless gas. Then this is lead 2 oxide. This is a yellow solid. This is a yellow solid. Then this is a gray solid, a gray metal. Okay, and again this is black. So the colors we are writing here, they help us to write the observations. Because a question can come asking you to write an equation when carbon reacts with zinc oxide. They ask you for an equation and also the observation. So you can come and write the equation, which is this one. Then you also write the observation. You would come and say a white solid turns to a gray solid and a colorless gas is evolved or produced. Am I clear there? Someone can say yes in the chat, then we move on. Yes, Nabu Kenya. Nabu Kenya, your hand is up. Let's hear from again, maybe from Jovia.
Excuse me, teacher.
Yes, please.
Had done for me the observation.
Okay. Then Agnes.
I said that carbon dioxide is colorless and oxygen is what?
Oxygen is also colorless, but we have different tests that we can carry out to differentiate between the two. We have many colorless gases, but we have specific tests of how we can test for such gases. Like I said, for carbon dioxide doesn't support burning. In other words, if you put anything burning, the fire will be put out, which is a different case with oxygen, which supports burning.
Okay, mister.
All right. Lastly, let me choose Agnes. I gave you a chance. Yes, Cravens.
What do you use to know that this is carbon dioxide?
Okay. So someone is asking what do we use to know that this is carbon dioxide. I say that we can have two tests. One, you can have a burning splint, anything, anything burning. Then you put it in a gas jar of carbon dioxide. Then the fire, if it has flame, the flames will be put out. They will just disappear, in simple words. Or we can use calcium hydroxide solution, which is colorless. The moment carbon dioxide gas passes through that solution, then the solution will turn from being colorless to it will turn to a milky suspension, or to turn milky. That is how we can confirm the presence of carbon dioxide. We shall have the details of that when we go to carbon dioxide as an oxide of carbon. Someone is asking, how do you know the colors? The colors, if you look at those, if you happen to go to the lab and you look at them, the powders, that's how you can tell the color. They will show you. They will be black. And when you hit, for example, zinc oxide, it will turn yellow. It will turn yellow. It will turn yellow on heating. It is just practical. So let me have the last question and we continue. This one, I don't know how to pronounce the name. Yes, please. What is your name? First tell us the name.
Kylie.
Yes, Kylie.
Teacher, another way to know that carbon dioxide is there, they tell us that carbon burns with an orange flame and makes bright sparks to form carbon dioxide. So if carbon burns with an orange flame and makes the bright sparks, you know that it is forming carbon dioxide.
Okay, thank you for that.
Oh, and go.
So members, let's continue. Kylie has given us another option of how we can test for carbon dioxide. We shall come to that. We shall come. Someone is asking if we can write the ionic equations of this. We can only have ionic equations. We cannot have ionic equations if we have aqueous solutions. As long as we have an aqueous solution, that's what we have an ionic equation. But if you have a solid, or you have a liquid, or a gas, these ones don't form ions. These ones don't form ions. Only aqueous solutions, as long as you find the word, this abbreviation of AQ. AQ is the one that can allow us to form ions. So here we cannot have ionic equations because of that. All these are gases, they are solids. They can't give us the ions. Let's look at a reaction of carbon with acids. So we can say that this is nitric acid, and sulfuric acid to nitrogen dioxide and sulfuric acid gases respectively. What do we mean here? It means that carbon can reduce sulfuric acid to form sulfur dioxide. Then it can reduce acid to form nitrogen dioxide. The amount of wood seems you are too late for that question. But if you have time, I'll see how I can repeat. And carbon, the carbon itself is oxidized to carbon dioxide gas. So let's see the equations and see how that one. So we can first remove these arrows. Okay. So we have this equation here. We are having carbon reacting with nitric acid, giving us nitrogen dioxide, carbon dioxide, and water. What does this mean? Yes, Joyce, I will send the work there. So we are now going to talk about this. We say that carbon reduces nitric acid to nitrogen dioxide. So this is where the other definition of someone said that a reducing agent meant that hydrogen to another or compound. So what happened is that carbon is away the oxygen from nitric acid, and when it does that, for it when it is going to form carbon dioxide. So after doing that, it will form carbon dioxide. And remember, now our nitric acid has lost this oxygen, so for it has been reduced to nitrogen dioxide. Then this hydrogen reacts with the remaining oxygen to give us water. And if you are to write the observations, this is a black solid. So what happens? It will dissolve. Carbon dissolves in nitric acid to give us, these are brown fumes. Remember, you should be writing these things down because they are not involved, they are not part of the notes, and that's why we always need to attend the live lessons. Whatever the observation we are writing and what you need to be writing. Solid, which is carbon, dissolves nitric acid to form brown fumes. Nitrogen dioxide, these are brown fumes. These are brown fumes. Then we say this is a colorless gas and also a colorless liquid. A colorless liquid. So this is a colorless liquid. So we can say colorless liquid. Colorless liquid. So this is a colorless liquid. And again here we said this is a colorless gas. A colorless gas. So we can come and say, let me first write the observation. We can come and solid, the black solid of dissolves to form brown fumes. Browns less Yes, hello.
Yes,
Sorry
I
for
can
that.
hear you.
Sorry for that. So members, the lesson is still on, but we are remaining with only 6 minutes. The lesson has not yet ended. It was just a technical issue. So let's utilize the remaining few minutes, which are like 6. So we're looking at the reactions of carbon with acids, and we had explained this one. Let's look at the second one. That is carbon reacting with sulfuric acid, and we say that the sulfuric acid will be reduced to sulfur dioxide, which is also a colorless gas, or at times they say white fumes, but it's a colorless gas also, and also carbon dioxide, which happens to be a colorless gas. So we have a black solid. We have a black solid. We have a black solid. Let's look at a reaction of carbon with steam. With the steam, there we mean gaseous water. That is when water is in a gaseous form. So if steam is blown through red hot charcoal, that is the same as when it is blown through hot carbon. A mixture of carbon monoxide and hydrogen gases are formed, and we call this mixture water gas. Normally this one comes in paper 1 in objectives, where they ask you which of the following gases form a water gas. So that would be hydrogen and carbon monoxide. So these two form what we call water gas. Yes. Sulaina Mugabe.
So there is a statement before your network went wrong. There is a statement that we are giving that the black solid of carbon dissolves. They stop there.
That's when I disappeared.
Yeah.
Someone had taken over and didn't allow me to come in. Okay, I'll put, I think because of time, I'll involve it in our notes that I will send to the Google Classroom. I was writing the observation.
Thank you, sir.
I'll write it in. I'll put it as part of the notes. Someone also asking for the same. You will get the notes. We shall send the notes in the Google Classroom. That's why you find your copy. So this is our equation. We are having water, or this is supposed to be a gas. This is supposed to be a gas, not a liquid. Reacts with the carbon to form carbon monoxide and also hydrogen gas. Remember, I said that these two, or this mixture, give us what we call a water gas. Oxides of carbon, we mainly have two. One, carbon monoxide. Secondly, we have, so these are the two main oxides of carbon dioxide, of carbon monoxide, which is CO, then carbon dioxide, which is CO2. Once again, like I said at the beginning of the lesson, carbon dioxide can be the same as carbon 4 oxide. And carbon monoxide can be the same as carbon 2 oxide, and I'd given an explanation for that. Let's look at carbon dioxide gas. Carbon dioxide is found in air. Carbon dioxide is found in air. And it occupies a percentage of 0.03% by volume. Then again, carbon dioxide, we can find it in rocks as a result of volcanic eruption. Then it also occurs in mines as chalk dump, and is also always present in natural drinking water because it is slightly soluble in water. So here we are trying to show how where we can find carbon dioxide. Let's look at laboratory preparation of carbon dioxide. What we see in the board are the words which are very important. So we are saying that carbon dioxide can be prepared by action of dilute hydrochloric acid on marble chips, and we are saying that marble chips that is a form of calcium carbonate. So we can as well substitute the word marble chips with calcium carbonate. Then we arrange the apparatus as shown below with calcium carbonate in a flask. Then we run dilute hydrochloric acid into the flask through the funnel. So what we do, we shall have the marble chips or calcium carbonate in the flask, and then onto them we add dilute hydrochloric acid through a funnel. So that is the equation, the diagram. So we are having dilute hydrochloric acid, which is going to be run through the funnel. Then we have calcium carbonate in the flask. So we shall add dilute hydrochloric acid onto the marble chips, or what we can call calcium carbonate, which are already in the flask. So on addition of that, we shall form a colorless gas. Which is collected over water, and that gas is carbon dioxide. So the gas we are preparing here is not dry. The reason it is collected over water, so we cannot have it dry, and also contains some impurities. Since we are using hydrochloric acid, normally hydrochloric acid contains hydrogen chloride gas. So to have a pure gas, we need to remove the hydrogen chloride gas, which is always with hydrochloric acid. Someone is saying that I'm too fast. It is because I want to cover something before we leave, but I will give more explanation in the classroom. If you have any questions, we can meet there and we explore more. It is also unfortunate that the lesson is ending and she's asking this. It is very unfortunate. And this is the same guy who had locked me out. Okay, let's have Navo Kenya. Navo Kenya. Same as Navo Kenya, it is hard for you to talk. Yes, Navo Kenya. Navo Kenya, can you speak up? Same with the network is too bad. So for more questions, if I'm very far, then we shall meet in the classroom, then I'll be able to explain. Sorry about that. So this is the diagram, and I say that this is for just carbon dioxide. It is not dry and it is not pure, and I say it contains hydrogen chloride gas. So we need to look at observations. When we see observations, we want to see what really happens. What can we see, or what we are able to see? What we are able to see. So what we shall see, this will happen in this one will have observations always here. What happens? We start with what happens where acid meets calcium carbonates. We're going to look. Yes, Jesse. Jesse, please. Yes, please. I know that you use the chat network is not all that clear. Use the chat, please. So we shall see effervescence of a careless gas being given off. So we shall see the gas, so bubbles of a careless gas in the flask. Then the equation. So this is calcium carbonate, which is in the flask. This is the one which is the flask, or what we call marble chips. Then we added hydrochloric acid. Then we shall form a careless solution, which is calcium chloride. Then the carbon dioxide we are interested in. And lastly, water.
Excuse me, sir.
Yes, please.
So when I want to check something on the chat, it tells me that Teacher Oswald is not in the meeting.
But when you send a message, I can see it.
But it doesn't.
Okay, because of time, I think we shall need to stop here. Then when we meet again, then we shall add on. But what I'm going to send in your classroom, it is the whole presentation of today. In other words, I'm going to send all these, they are around, there are 14 slides. So far we had stopped here. So I will send also this one, and also I'd attach the video that you watch. So because of time, you allow me to stop here, and we shall explore more in our classroom. Can we have a closing prayer, Agnes? If you have a question, you can ask, then you also give us a closing prayer. Agnes?
Mr. I just want to if we use
Agnes, you're not here.
concentrated acid for drying carbon dioxide.
Agnes, I was not hearing you. Let's have Ashley. Ashley, give us a closing prayer.
Okay. Loving Jesus, we want to thank you for this lesson that we just had. We want to thank you for guiding us and protecting our teacher, oh Lord Father. We want to thank you for this lesson that you've given unto us. Let each and every student who has attended this lesson go out with something. Let them go out with everything they have understood. I've prayed all this believing and trusting in your son Jesus Christ. We prayed. Amen.
Amen. So have a good day and a nice